Greetings. We will begin with unit 5 in today's class, and this is an interesting topic because we will be talking about pseudo forces, and the word pseudo suggests that there is something unreal about it, and then we will see that they generate real effects. So that is part of the reason that some of my students and I, when we were talking about it, we decided that we will call this as real effects of pseudo forces. So we will learn about moving coordinate systems, and in particular our focus will be on understanding what is meant by an inertial frame of reference as opposed to a non-inertial frame of reference. We will spend some time assimilating our understanding of the deterministic cause effect relationship in an inertial frame of reference and how this idea can be modified in a non-inertial frame. So there are important contributions due to Gaspard Coriolis, and it is always said that Newton's laws hold only in an inertial frame of reference, and we need to understand exactly what this means. The reason this is so important, despite the fact that there is early introduction to this idea in the schools and even in 7th or 8th grade school education, one learns about Newton's laws and one learns statements of this kind, that Newton's laws hold in an inertial frame of reference. And at this course, which is in this course which is designed for the first year students in after the high school in college, I would like to spend some time discussing this idea further. The reason is this idea is extremely fundamental, and what it will tell us is what we call as a force, or in modern language what we call as an interaction. I mean, this idea of a fundamental interaction, what is a fundamental interaction at all, and that is what physics is about. Physics is about exploring fundamental laws of nature. And what is a fundamental interaction is something that we really need to understand, and this understanding is incomplete without a very deep understanding of Newton's laws, and in particular remarks of this kind that Newton's laws hold only in an inertial frame of reference. The fundamental forces that we understand and that we make use of in modern physics are electromagnetic forces, electroweak forces, nuclear strong or nuclear weak interaction, or the electroweak interaction if you talk about the unification between the nuclear weak interaction and the electromagnetic interaction. And then there is gravity, which sticks out, which continues to pose a major challenge. And then we also make use of pseudo forces, which are not fundamental forces, but then they are forces nevertheless. And then there are other forces that we talk about, like friction and so on, and we really need a very clear understanding of the differences between these, because most often we do work in non-inertial frames of references, and yet we seek a causality. So if causality is to be reactivated in frames of references which are not inertial frame of references, then how would we do it? So these are some very subtle questions, simple nevertheless very subtle, which is why they do seek if further discussion. So these are some of the ideas that we shall be discussing in this unit. Now, what is it that we regard as an inertial frame of reference? How do we define an inertial frame of reference? and very often the textbook definition in the schools is not very useful in this particular situation, because in a textbook your inertial frame of reference is often defined as one in which Newton's laws hold, or else it is defined as one which moves with respect to another inertial frame of reference at a constant velocity, and neither of these two definitions seem to help very much if you really ask what is it that these definitions really mean. And what we have to admit as a starting point is the Galileo's interpretation of inertia, that motion is self sustaining in an inertial frame of reference if it is determined completely by initial conditions, and initial conditions alone determine the motion completely. Now, if this is what happens in a frame of reference that you are in, then you could conclude that you are in an inertial frame of reference. So, the essential criterion that I would like to highlight is that in this frame of reference motion is determined entirely by initial conditions alone. And this is particularly useful as opposed to some of the other criteria which are invoked to reference what an inertial frame of reference is, or to point out what an inertial frame of reference is. This question of course was important for Galileo, it was important for Newton, and the early idea that Newton envisaged was that an inertial frame of reference is situated in deep space amidst distant stars. Now, this is in a certain sense a very romantic idea, it is almost poetry, that the inertial frame of reference is situated in deep space, and then to address Newton's romance it sort of descends on earth, and it reminds me of this song from the movie Kabhi Kabhi, in which he says that tu ab se pehle sitaron mein bas rahi thi kahin, tujhe zameen pe bulaya gaya hai mere liye. You know, it is like a frame of reference, it is situated deep amid stars, and then it descends on earth just to address Newton's needs or Galileo's needs to have an inertial frame of reference. But there is more to this than just poetry and romance, and that is what we need to talk about. So, we have agreed that we will recognize an inertial frame of reference as one in which motion, the evolution of a system, the temporal evolution, the time evolution of the mechanical state of a system is completely determined by initial conditions. And let us consider this red frame of reference. This is a Cartesian frame of reference x, y and z, and this carries a subscript I to tell us that this is the frame of reference that we will regard as the inertial frame of reference. And let us now talk about another frame of reference whose origin O prime moves with respect to the origin of this inertial frame of reference, which is OI, and this moves at a constant velocity, so that the displacement vector between the two origins is equal to this ut, where u or u subscript c is the constant velocity of the frame f prime with respect to f. Now, how do these two observers, an observer in the red frame which we have identified as the inertial frame of reference as one in which motion is determined entirely by initial conditions, how do the observations of an observer in the inertial frame, which is the red frame, which is the frame F, compare with the observations made by another observer in the frame F prime. So, the observer looks at an object whose position vector in his frame of reference is r t, and this object has got a different position vector which is r prime in the frame F prime. So, you can use this triangle law of addition, and you know that these two vectors r and r prime are related to each other through this displacement vector O O prime, which is u c times the time that has elapsed since the frame of reference F prime crosses the point O I. Okay. So, that is the model we have in mind. Now, for simplicity we assume that the frames of references have their coordinate axes which are mutually parallel to each other, so that the x prime is along x, y prime is along y, and so on. But the only thing is that at what we will call as time 0, which is the reference time from which we start observing the system evolution, O prime gets separated from O I and it starts moving at a constant velocity u c. So, that is our conjecture, and if you differentiate this with respect to time, and this is within the realm of what we call as Galilean relativity, and in Galilean relativity this time has got an absolute significance in both the frames of references. You do not need to modify the perception of time in the blue frame as it is in the red frame. This is an anticipation of what we shall discuss in the next unit, which is unit 6, in which we will discuss the special theory of relativity, and in which we will make use of the Lorentz transformations, in which time itself needs to be modified as you go to another frame of reference. So, that idea is not involved over here. This is the pre-relativistic transformation. This is what we call as the Galilean transformation, and in this time is the same for both the observers, and you take the derivative with respect to time to get the corresponding velocities, and you get a relationship between the velocity as will be observed by an observer in the frame F, and compare it with the velocity of the same object as is seen by the observer in the frame F prime. Now, obviously you see that the first derivative is different, okay, the two velocities are different, and the difference is by this constant velocity u. This comes from a simple differentiation with respect to time. The velocities are different, but what is the big deal? If the velocities are different, it does not change the perception of equilibrium in the two frames of references, because we already learned from Galileo's law of inertia that a state of rest and of uniform motion are completely equivalent to each other, and these do not require any cause. In these states, motion is determined completely by initial conditions. A cause will be required only when equilibrium is disturbed, and the detection of the change in equilibrium will be in terms of the second derivative of the position vector, not the first. The first derivative is what gives you the velocity, and if the two velocities are different, no big deal about it. But to see if there is any departure from equilibrium, we must look at the second derivative. So, we now look at the second derivative, which is d2r by dt2, this which is the acceleration perceived by an observer in the frame of reference F, and he finds that it is exactly the same as it is for an observer in the blue frame, which is moving at a constant velocity. The two accelerations are exactly the same, which really means that it is the departure from equilibrium. If this is what interests the two observers, they will not have to invoke different laws, because what they measure for acceleration in their respective frames of references is essentially the same. Acceleration in the red frame, in the frame inertial frame, is exactly equal to the acceleration in the blue frame, which is moving with respect to the red frame at a constant velocity. A is equal to A prime, which necessarily means that if you just scale it by a scalar, which is inertia, which is the mass, then the equation F equal to ma and ma prime equal to F prime, each of these terms is exactly equal to any of the other terms. So, F is equal to ma, which is equal to ma prime, which is equal to F prime. All the four quantities that you see, the two forces F and F prime and the two accelerations A and A prime, scaled by the same mass, which of course remains invariant when you go from one frame to another. A mass is a excellent scalar, it is completely invariant, which means that the laws of mechanics are exactly the same in these two frames of references, and you can therefore call the frame of reference F prime also as an inertial frame of reference, because the same law of physics is to be invoked in explaining the acceleration. This is what justifies the definition, the high school definition, that an inertial frame of reference is one which moves with respect to another inertial frame of reference at a constant velocity. Okay, this definition by itself does not mean very much, but it makes perfect sense once you understand that the laws of mechanics turn out to be the same in such frames of references which are moving with respect to each other by a constant velocity alone, because the linear response which Newton invoked, or rather Newton invented, and this is really very fascinating because we are making use of calculus, we are talking about the first derivative, the second derivative, and calculus really did not exist before Newton. Newton was just about 21, 22 years old when he was observing planetary motion, and to understand the angular orientations of these planets he needed geometry, he needed trigonometry, and then he needed some idea of the rate at which these positions change with time, and the idea of rate, which is what we are so familiar with because they teach us derivative in our mathematics classes. So, we know what a derivative of a function is, we know that this can be defined only when you construct a function, you need the function to be continuous. So, you need the idea of a limit, and then you take the change in the value of the function at two neighboring points, divide it by the independent parameter difference, and then take the limit that the independent parameter difference goes to 0. Now, these ideas of limits and derivatives really did not exist before Newton, but Newton invented this. He invented calculus, and then he explained that when there is a departure from equilibrium, it results as acceleration, which is the second derivative of the position vector, and this is then the result of some reason. This is where you need to look for a reason. As long as you do not find acceleration, you do not find that the second derivative is non-zero, you are looking only at equilibrium, and that does not seek a cause at all, because it is completely determined by initial conditions. You do not have to look for any cause, but when there is a departure from equilibrium, you must look for a cause, and this then results in the acceleration. So, acceleration is then the effect of a certain cause, and you must look for this cause. It is this cause which Newton called as force, and Newton went on to tell us that the result, which is acceleration, is linearly proportional to the cause, which is a force. So, this is a linear response theory. You have got a stimulus which is a force. In modern language we call this as an interaction. So, this is the stimulus, and to this stimulus the mechanical system responds by changing its state of equilibrium, which manifests as an acceleration, and this acceleration is linearly proportional to the stimulus. The proportionality is the inertia. So, F equal to ma, which is a linear equation, m being the mass, which is what we also call as the inertia of the system, and this is a complete statement of the linear response mechanism which takes place between the stimulus, which is a physical interaction or the force, and the response, which is observed as an acceleration of the mechanical system. Now, what is fascinating is that the same linear response mechanism, f equal to ma or f prime equal to ma prime, exactly the same relationship holds in both of these frames of references, namely the blue frame of reference, which moves with respect to the red frame of reference at a constant velocity. Okay. So, the same cause effect relationship, and this is the meaning of the statement that the physics is the same in all inertial frames of references, because the same physical interaction explains the dynamics. It explains the departure from equilibrium. Galileo's understanding of inertia, of course, was fundamental, and Galileo came before Newton. Newton was born the year Galileo died in 1642, and Galileo had recognized that the state of rest or of uniform motion are completely equivalent, and he did it by carrying out these experiments by rolling these spherical wooden objects on inclined planes, or by dropping objects from the top of a mast of a ship, and whether you drop it when the ship is in motion, or if it is docked, or if it is anchored at some place, it falls at the same relative place. And by observing this, Galileo recognized the law of inertia, which is really very fascinating, because it is completely counterintuitive. It is completely counterintuitive, and Galileo recognized this, and Newton factored it in his understanding of how a mechanical system evolves with time, and if it is in a state of equilibrium, then the initial conditions alone determine the evolution. If there is a departure from equilibrium, then Newton recognized that there must be a cause which will generate the effect which is observed. The effect that is observed is the acceleration, and the effect is directly proportional to the cause in this stimulus response linear response mechanism. This is the principle of causality or determinism in classical mechanics. Now, this immediately tells us that mass and weight are different things. Mass is actually the proportionality which goes into the stimulus response relationship. When the response is provoked by a cause which happens to be gravity, then the interaction or the force is called as the weight, and the response, which is acceleration, this is due to gravity, so it is called as acceleration due to gravity. So, this is the relationship between mass and weight, a term which we abuse left, right and center, because every time people want to point out to me, which for good reasons, that I have grown fat, they always tell me that your weight seems to have increased. What they really mean is that the mass has increased. Mass is the actual quantity of matter. So, it is not a bad idea to quickly do a couple of lunatic exercises, and we will ask if lifting a cow is easier on the moon. Okay? It looks like a totally crazy idea. Lifting a cow on the earth is crazy enough, and lifting it on the moon is even more so, I would think. And actually a cow can be lifted. There are these commercial cow cradles which are available, and one can actually purchase it. And you know the answer, but I raise these questions not to discuss them in the class, but just to highlight the difference between mass and weight, because on moon the gravity would be a little weaker. So, here you see this lady lifting the cow, but I am afraid she is not lifting, she is probably preventing the cow from flying off, because it is probably filled in with some gas that you kind of put in a balloon. So, she is not just lifting it, but so these are fun lunatic exercises as we call them. Let us do one more. If it is easier to stop a charging bull on the moon, and this is a lovely painting by Russian painter Sorokin. This is a beautiful painting, and the question here is it easier to stop a charging bull on the moon? And I will let you think about it. So, now we really understand, we are in a position to understand what exactly is meant by a physical cause, what is meant by an interaction. A cause is the physical agency which generates an effect. Simple. The effect is measured in terms of departure from equilibrium, because the state of equilibrium seeks no cause, it is self sustaining, it is determined completely by initial conditions. That is the first law of inertia. It is only the departure from equilibrium, only when the momentum changes, as long as the object continues to move at a constant momentum, you seek no cause, it is completely determined by initial conditions. And then you must seek a cause only when you observe a departure from equilibrium, and this cause is what we will call as a force or a fundamental interaction, and this can belong to only one of the four fundamental categories. It can be either an electromagnetic interaction or a gravitational interaction or a nuclear strong or a nuclear weak. And of course, modern physics aims at unification of these forces, which is an attempt to understand that all of these forces are different expressions, different manifestations of the same fundamental interaction, which is what is meant by unification. So, the cause which will go into the stimulus response theory will have to be a physical interaction. It will have to be one of these four fundamental forces, or if you do not want to call them as four, because electromagnetic and weak interaction has already been unified, then depending on the level of unification the number would be less than 4, anything from 1 to 4, but it cannot exceed 4. So, these fundamental forces can be understood only in terms of this idea which we learn very easily in our high schools, but it really has a very deep impact on physics. Of course, quantum theory makes the discussion quite complex. So, it is no more in terms of the stimulus response in the kind of the differential equation that you see from Newtonian dynamics, but the basic idea of a fundamental interaction still remains the same. And which is part of the reason that this idea really needs a careful discussion in college physics as well. And now we understand the meaning of this statement that an inertial frame of reference is one in which Newton's laws hold, because this statement is cast in the context of this entire discussion that we have just had. All that discussion goes in the background, or it provides the platform for developing what is a very simple statement that an inertial frame of reference is one in which Newton's laws hold. But without this discussion, this statement really does not tell us very much. It is just like a definition. Now, in the previous frame of reference, in the previous case we compared observations in two frames of references, the red frame and the blue frame, and the blue frame was moving with respect to the red frame at a constant velocity. Now, we will let the second frame move not at a constant velocity, but we will let it undergo an acceleration with respect to the inertial frame. So, that brings us to discussing physics in an accelerated frame of reference. The question that we are going to have to raise is, what will happen to the cause effect relationship? Will causality and determinism survive? Do these ideas survive in an accelerated frame of reference? And the answer is both yes and no, and I will explain why it is yes and why it is no when we discuss it further. So, let us now construct a frame of reference which is this green frame, and this frame f double prime, this moves with respect to the frame O, and let us say at t equal to 0, which is just when you start the clocks in the two frames of references, and these clocks are Galilean clocks, these are not Lorentz clocks. These, the Lorentz relativity is what we will discuss in the next unit, which is unit 6. We are now in the realm of Galilean relativity. The two clocks, they remain synchronized in Galilean relativity, and when you start the clock, the green frame and the red frame, let us say that they are on top of each other, and at t equal to 0, the green frame shoots off with a certain initial velocity u I and a constant acceleration which is not 0 now. In the previous case it was 0, now it is not. So, f is some constant acceleration. So, the displacement vector between O and O double prime is obviously equal to UIT minus half FT square. This comes from elementary kinematical equations. And now you consider motion seen by an observer in the red frame, in the inertial frame of a certain object which is here, whose position vector in the inertial frame is r, and in the accelerated frame this position vector is r double prime, and the two are related to each other by the triangle law of addition. So, r of t is equal to O prime, which is this vector from O to O double prime, plus this green vector. So, O double prime plus r double prime is equal to r. So, this is the relationship that we get, and O double prime, this is the displacement vector which is already seen to be UIT plus half FT square. So, this is our basic construct. Now, to get the velocity, you take the first derivative with respect to time. So, this is a simple differentiation. On the left hand side you get dr by dt, from differentiating uit you get ui, by differentiating half f t square you get f times t, the factor 2 will cancel in the denominator and this one, and then you get the velocity as seen in the double prime frame of reference, which is d by dt of r double prime. If you now take the second derivative, you will get the acceleration, and that is what will be a measure of departure from equilibrium, and this is where you are going to look for a cause. So, you take the second derivative. So, here you have the second derivative on the left hand side, and on the right hand side the derivative of ui vanishes because it is just the initial velocity, which is some constant number. So, its derivative with respect to time will vanish, and from the derivative of f t you get f, and then you get the second derivative as seen in the double primed or the accelerated frame of reference. In other words, the acceleration in the frame red is not equal to the acceleration in the accelerated frame. The acceleration of the object under investigation, which is this object over here, this is the object whose mechanical state is being observed by two observers, and the acceleration of this object is different in the two frames of references. A is not equal to a double prime, the relationship between them is a is equal to a double prime plus f. So, now the observer in this green frame, which is the accelerated frame, what is he thinking? He measures an acceleration in his frame which is a double prime, and it is equal to a minus f. So, m a double prime, if you just multiply this by the inertia of the system, which is the mass of the system, m a double prime is equal to m a minus m f, and this is what the observer in the green frame will recognize as the force. So, his idea of force is not the same as the idea of force in the inertial frame of reference. In other words, if m a, which is the mass times acceleration, is what we regarded to be equal to the physical interaction from Newtonian dynamics in the inertial frame of reference, and if this is what gave us our idea of force, if this is what gives us our idea of force, no matter what its form is, electromagnetic, nuclear strong or weak, or gravity, it cannot be anything else, it has to be one of these. And if this is what is recognized as force, then this quantity over here is obviously not a fundamental force, because a fundamental force, the idea of fundamental force was developed in the inertial frame of reference. But to the observer in this double prime frame of reference, which is what we call as the accelerated frame of reference, to this observer the acceleration a double prime is a completely real phenomenon, it is a measurable thing, it is what he measures in his own frame of reference as a departure from equilibrium, and he finds that it is equal to mass times acceleration in the inertial frame less and a constant quantity which is m times the little f. And if this has already been identified as the fundamental interaction, then this is obviously just a mathematical artifact of the fact that this frame of reference is accelerated with respect to this, there is no physics in it. It is not the result of a physical interaction, it is the result of carrying out observations in a frame of reference which is not an inertial frame of reference. So, whenever you do that, you will find that the mass times acceleration in an accelerated frame of reference will not be equal to the physical force, but it will be different, and the difference in this case is what I have written as F with a subscript pseudo, because it is not a real force. What happens to the principle of causality? The cause effect relationship, which was a linear response equation, acceleration was proportional to the cause, right, and the proportionality was the inertia. Now, that relation has to be modified, and you can sort of modify that relationship by inventing this F double prime, which is the difference between F and this MF, which is F pseudo, and this difference is what you can call as the net pseudo force, which includes the real interaction to a certain extent, but it also includes a mathematical construct of the fact that observations are being carried out in an accelerated frame of reference. So, the same cause effect relationship which explained dynamics in the inertial frame of reference does not do so anymore in the accelerated frame of reference, which also means that the laws of mechanics are not the same in these two frames of references, and this is the meaning of the statement that an inertial frame of reference is one in which the laws of mechanics hold. And now we see what that statement really means, because we find that the laws of mechanics cannot be stated in the same form, they must be modified if you have to recast them in an inertial frame of reference, in an accelerated frame of reference. So, this is what we call as the real effects of a pseudo force, because the observation A double prime is very much real to the observer in the accelerated frame of reference. You can write F double prime equal to M A double prime, in which this is now your idea of the physical interaction, but this idea of the physical interaction includes the real force F less a force which is not a physical interaction. F pseudo cannot be reduced to any fundamental force like electromagnetic or gravity or nuclear strong or weak. And I will invite you to read this article which some of my students have written. In particular, Gopal Pandurangan was the first one to do this, and subsequently this work was done also by Chaitanya and Srinivas Murthy, and this article is available at this link. And this is the title of this paper, that what you see are real effects of pseudo forces. The effects are real, the cause is not. So, you can sort of restate the deterministic cause effect relationship, which really holds only in an inertial frame of reference. It is this relationship which generates in our mind an intuitive perception of what a fundamental force is, and once we recognize this idea of a fundamental force, then we only study its form, whether it is electromagnetic or nuclear or gravity or some unification thereof. These are different forms, but the idea of a fundamental interaction comes essentially from the perception of an inertial frame of reference. And if you want to somehow force causality in a frame of reference which is accelerated, because you always like to reason out. In classical mechanics, the entire domain of classical mechanics is inspired by causality, that you look for causes, you think that okay, there is a cause which explains the result, So, if you seek similar relations in an accelerated frame of reference, then you can do so only by inventing causes which do not exist. Okay, these are the pseudo forces. So, you can invent these pseudo forces, these are fictitious forces, and obviously Newton's laws are not designed for these fictitious forces. So, they can be used in some sort of Newtonian formulation of mechanics, but they will include these pseudo forces which are forced into our thinking by the fact that we are explaining observations in an accelerated frame of reference. So, there are related issues like people talk about weightlessness, and you experience this all the time. Means if you carry a weighing machine with you in the elevator when you come to this floor, we are now on the 3rd floor, and this experiment is more interesting when the elevator is accelerated rapidly, or while going down it is again accelerated, but the direction of acceleration is different. So, in one case when the elevator is going up, the acceleration is against gravity, when it is going down it is in the same direction as gravity, and if you weigh yourself on a weighing machine, you are going to record different weights. So, the idea of weightlessness is connected to the fact that observations in an accelerated frame of reference will not be explainable, they will not be explicable in terms of the same fundamental interactions which are invoked in an inertial frame of reference. And this is in fact very nicely exploited by sports people. I mean, here is a picture of Sergei Bubka who retired, but one of the most famous pole vaulters of all times. Now, look at the elegance with which he goes over the bar, and by flexing his body, means he has got his arms and limbs which he can position. I can hold my hand here, I can hold it here, and I can hold it here, but where I am holding it will determine where my center of mass is. Okay. Unfortunately, it will not reduce my mass, but at least it can change the position of the center of mass, and that can be done simply by changing the position of my limbs, right. So, what he manages to do is by flexing his body, he can let the center of mass go a little bit lower than where he otherwise has to raise the entire body to that point. If he wants to clear a certain point, okay, he can in principle allow the center of mass to actually go below the bar and let the body go above the bar, as long as he can flex his body suitably, and the energy he needs to raise the center of mass above the bar is obviously much more than what is required to raise it to a point below the bar. Now, I do not know if where his center of mass actually goes by, does it go below the bar or above the bar, that is a matter of detail, but it is quite clear from this discussion that it is not necessary to raise it to the highest point. You can let it go at a lower point, and this becomes possible because his control on his limbs is so easier in this state, because he is in a state of what we call as weightlessness. Okay, he is in a state of free fall, all parts of his body are falling at acceleration due to gravity at g. Okay. So, what he has to overcome is just the inertia of this part of his body by his muscle power, and not the weight of this. Okay, that is the difference between mass and weight. He has to manipulate just the mass and not the weight, because the entire body is in a state of weightlessness, it is in a state of free fall. So he can exploit it, and athletes do it very nicely, and Sergei Bubka is one of the best known pole vaulters, so I had his picture, but maybe you are familiar with some of the modern pole vaulters, and this is the one who got the Olympics gold medal in 2008, Yelena Isinbayeva. How do you pronounce it? Vivek, do you know how to pronounce it? I don't either. This is a Russian name, and she cleared 5.05 meters in the 2008 Olympics, and exactly the same thing. I mean, the kind of agility these athletes have in manipulating their limbs is what distinguishes them from ordinary people. So I guess we will take a break here. If there is any question, I will be happy to take it, otherwise we will take a break and we will continue from this point. And in the next class we will continue the discussion on real effects of pseudo forces.